Okay, so we are starting chapter 3 here for week 2, graphical methods of describing data. And there are going to be several things organizing that have to take place first before we can construct those graphs. We'll cover those here as well. So let's start out talking about organizing and graphing categorical data. I'm assuming that you guys are all familiar with bar charts. So we're looking at variations of the bar chart, the double bar chart. When would we use this? Of course, it's with categorical data, and we're looking at comparing multiple sets, 2 or more sets of data in a single chart. So how do we construct it? Well, it's just like constructing a bar chart, but with 2 or more groups being compared. We must have either use relative frequencies on the vertical axis, or we can use, if the frequencies are close, we could still use raw frequencies. But why do we say that we use the relative frequencies? Because we include if the frequencies are different, they're not going to fit on the same axis. It's going to be hard to compare. Also, we must include a key that shows which bars represents which data sets, whether it's color-coded or labeled in some other way. So for example here, each year the Princeton Review conducts a survey of students applying to college and of parents of college applicants. In 2009, 12,715 high school students responded to the question. Ideally, how far from home would you like the college you attend to be? Also, 3,007 parents of students applying to college responded to the same question. How far from home would you like the college your children attends to be? Data is displayed in the frequency below. So here's an example of why it is that we have to do the relative frequency is, well, here there's 4,500 students compared to only 1,500 parents, or sorry, in the less than 250 miles. For a total, there was 12,000 students, only 3,000 parents. That's 4 times as many. The bars would be way out of whack. So in order to make it an accurate comparison, we're looking at relative frequency. So what do we do first? We find the relative frequency. Remember, if you don't remember how to do relative frequency, you'd have to take the total of the column and then divide each number in the column by that total. So basically this is saying 34% or 35% of students want to be less than 250 miles away from home, while 53% of parents want their child less than 250 miles from home. So again, we found that by dividing the frequency by the total for each column. So then we construct the double bar graph. And notice there's a key here. The blue represents the student's response, red is the parents'. And because we did the relative frequencies, this is an accurate comparison of the percent of each. The only way that we can get away with using raw frequencies is if the total number from each category were exactly the same. If they interviewed exactly the same number of parents as they did students, then we could do just raw frequency. That's the only way that works. Otherwise, we have to use that relative frequency. So we have a segmented or stacked bar graph. These work best when you're obviously still with categorical data, but when you have each item can be broken down into different related subcategories. So again, we first calculate relative frequencies, draw the bar representing 100% of the group, and then divide that bar into the segments based on the relative frequencies. So in this case, here's our data from the distance from home for colleges. We first draw a bar that represents 100% of the students who answered the survey. So that's all the students. Next, we divide it into segments. Well, if that represents 100% or 1, 35% or 0.35 is going to be less than 250 from home. So you can see that bottom there is the less than 250 miles. That's 35%. 31% is the red. That's the 250 to 50 or 500 miles from home. That's a little bit smaller, 31%. Just a little smaller than the blue. And then smaller yet, the 500 to 1,000 is that 19%, and so on. And we do the same for the parents. Represent 100. Now, obviously, 53%, bigger portion want their child to stay closer to home. And then we do have to provide a key. Here we give the color code saying what each color represents. Notice it's the same relationship. You can see more parents want their kids closer to home, and fewer want them further away compared to the child themselves. There's a pie chart or circle graph. How do we use this? This again is categorical data. We draw a circle that represents 100% or the whole thing. We divide it into 360 degrees, and then we use relative frequency to figure out how many degrees. The relative frequency times 360 tells us how many degrees each slice of that pie is going to be. Now, realistically, I haven't actually pulled out a protractor and measured degrees on a pie chart in a lot of years. We have software that does that for us. We're not going to make you do it by hand in this class. The software will do it. Realistically, if I'm doing this by hand, I'm just looking at benchmarks, knowing that half a circle is like 50%, quarter of a circle is 25%, and I'm kind of guessing from there. I might say, okay, 31% was a little bit more than a quarter, that's the 31%. 35 is a little bit more than a quarter, and I'm just estimating them in, because if I want that perfect pie chart or circle graph, I've got software to do that for me. So measuring out with a protractor is not something we really do anymore. Then you need to make sure you have each category labeled or a key of some sort of legend telling which one is which. So here we go again. Here's our number of typos in typing a resume. 1, 2, 3, 4 or more, or don't know. The raw frequencies are in there, and we did calculate the relative frequency for each. Now that 0.40 is 40%, so that's going to be a little bit less than half of the pie chart. So we've got those relative frequencies. We draw a full circle, and then our first slice, 40%. 0.4 times 360 is 144 degrees. So if you were using a protractor, you would measure out 144 degrees there. And then putting in the rest of them. And notice each of them was labeled. This is 1 typo, 2 typos, 3 typos, 4 typos. Don't know how many typos. And then the percent is actually given as well. You don't have to give the percent, but in this case, we got some bars that are kind of close to the same size. It's helpful to have that in there to tell, is there more that had 1 typo or 2 typos, because those are really close together. So what does this pie chart tell us about the number of typos in a resume? Well, 1 is definitely the most, but 2 is a close second, and a large majority of them have 1 or 2. There's very few, a very small portion that have more than 2 typos. Now let's look at describing numerical data with a graph. So these are different dot plots. This is another dot plot here, data set B, using the same number line axis, translating those up, and this is another one, C, using the same number line axis. This is sometimes referred to as a comparative dot plot, so you have different sets of data on a single axis so that you can compare them better. Here we're comparing the exam scores for 3 different classes. We're just calling them classes A, B, and C. Obviously, by looking at this comparative dot plot, we can see that Class C has much higher scores. I mean, their lowest score is higher than the highest score for Class A. We can also see the shape of the distribution. Each of these kind of forms that little bell curve, that normal distribution. The center of it, this one's approximately 66, 67. Center of this one's going to be up there 77, 78. This one looking at 86, 87, somewhere in there. That's describing the center. And there are going to be several measures of center we look at when we look at calculating data. For now, we're just looking at that and kind of saying, what is about the middle of that curve? We said that I mentioned the term bell curve. The middle of the curve would be the point where I could fold one side over onto the other. It'd be symmetrical about that. That's about the center of that curve. There are three measures of central tendency that we're going to talk about: mean, median, and mode. Notice the mode is in green because the mean and the median are typically the most important. The mode is the number that occurs the most often. In small sets of data, it really isn't, a lot of times there isn't even a mode because there's no numbers that are repeated. But the mode is really only useful if really a large set of data, so a large data set, or it can be used for categorical data. If I ask you what your favorite color is, red, blue, or green, or what preference of color, red, blue, or green, like we put in last week, you can't calculate a mean or a median of that because there's not numbers, but you can calculate a mode, which color was picked the most often. So typically for numerical data, we worry about the mean and the median. The mode is not that important. So what strikes you as distinctive difference between the distributions of these scores if we do three other classes, D, E, and F? Well, now the center of all of them seems to be in about the same spot, about that 69, 68, somewhere in there. But we can see class F covers the whole width of that number line. Class E is a little less rangy, has more compact together, less spread out. And class F is way more closer together, way less spread out. So this idea is actually spread, sometimes called dispersion. Some textbooks use that term, just how dispersed it is, which again means spread out. So discuss how spread out the data is. We have several things that we'll use for that. Range, variation or variance, and standard deviation. It refers to how the variability of the data. How, if we're randomly selecting an item out of this data, how variable, how far apart do we expect the successive choices to be? How much do we expect that choice to jump around? Measures of spread, distinctively, we mentioned range. That's how spread out they are. Standard deviation and variance kind of go together. Variance is calculated in the process of calculating standard deviation. IQR stands for interquartile range. For that to make much sense, we need to discuss how to calculate the quartiles. Quartiles are a measure of position, but the distance between them is a measure of spread. So the range is just largest value minus the smallest value. I'm sure you've seen that. IQR we're going to discuss in the next PowerPoint for Chapter 4. Standard deviation as well. It's a longer calculation. So when we look at describing data numerically, we'll look at those calculations. So now here, when we look at these data sets, this bottom data set has that bell curve we were talking about. These other ones have one tail or the other stretched way out. This one's stretched out in that direction. This one is stretched out on that right end. This is called, of course they'll draw in the curves for me better than I did probably. The shape of the data, whether it's symmetrical or the term we're going to use is skewed, refers to the overall shape of the distribution. Is it symmetrical? Uniform, now we haven't seen a uniform one yet. Uniform would be if we had all the dots basically the same height at every value. So it looked like a rectangle rather than that bell curve. And skewed. So skewed is when one of the ends is stretched out, like the top two data sets were. Bimodal, we didn't see example of that. Bimodal would actually have like two humps in it, like that. So let's discuss these in more detail. So let's collect data by rolling two die and recording the sum of the two die. We're going to repeat this a few times. Plot your sums on the dot plot on the board, and what shape does this distribution have? Well, we're not in a physical classroom, so we're not going to do this as a class. We'll do this now here as part of the PowerPoint. Symmetrical data refers to data in which both sides are more or less the same shape. So if I have my bell curve like that, not a great artist, but I think that'll work. If I cut it down the middle, if I take this shape here and I flip it over, it should fit right on top of that shape, pretty much fit right on top of that shape there. That's symmetrical. Bell-shaped is typically what we use. Bell-shaped goes with what we refer to as the normal curve or normal distribution. We call it normally distributed. We'll talk more about normal distributions right later in the course. Now we're going to, so that was what the data would we got if we rolled those two dice and added them together. Now we're going to collect data by rolling a single die and recording the numbers rolled. We're going to repeat this over several times and plot them on the board. What shape does this distribution take? Well, it's a uniform distribution because the values 1, 2, 3, 4, 5, and 6 are equally likely to occur. The number of dots above each value should be, on average, about the same. So it's just forming that rectangle shape. So to help remember the name for this shape, picture soldiers standing in straight lines. What are they wearing? Well, they're all wearing their helmets, whatever, using the exact flat surface. So they have a flat top on top of them. So that's that flat-topped uniform distribution. Our next example, we're going to collect data by finding the age of 5 coins in circulation. So you're going to grab a handful of coins out of your pocket and look at the date in which they were minted, the date printed on them. And again, we're going to use a dot plot. We're going to, rather than the date, we're going to look at their age, so how many years it's been since they were minted. So if it was minted in 2018, this is 2020, so its age would be 2. This would make a skewed data. Most of those coins are going to be pretty new, and there's going to be a few that are older, and they're going to be way spread out as they get older. So it's going to form that curve like we saw with the tail way stretched out on one end. So skewed refers to data in which one of the tails, one side, is stretched out longer than the other. If it's stretched out this way, it's called skewed right, because it is the right end of that curve that is stretched out. So the skewness is the direction in which the longer tail is. So if it's like this, that would be skewed left, because the longer tail is to the left side. So the directions are positive, right, or negative to the left. Name a variable with a distribution that is negatively skewed. One example I can think of might be age of college students. There are a few that are younger, down into that 16, 17 age, maybe even 15, but most of them are right in that older age group, that higher age group. Now let's look at, suppose we're going to collect data on the time it takes to drive from San Luis Obispo, California, to Monterey, California. That's where the authors of our textbook are from. That's where they're using California. Some people may take the inland route, approximately 2.5 hours, while others may take the coastal route, 3.5 to 4 hours. What shape would this distribution have? Now, those that take the inland route, they are not going to take exactly 2.5 hours. Some will take longer, some will take less time. If we did that on a number line, 2.5, 2.5 would be in the middle here, and we would have that bell shape if that was just the ones doing the 2.5 hours. If we did the ones taking that 3.5 to 4 hours, again, the average would be in that 3.5 to 4 hours, but some would take less, some would take more. If we put the two of these together, we're going to get a distribution that's bimodal. What that means is we overlap those two. There's 2.5 here. There's 3.5 to 4.0 over here. We've got a hump at 2.5. There's some that are going to take in the middle there, but it goes way down. Some of the people from the 2.5 hour route take way longer. Some people from the 3.5 to 4 hour route get there a lot quicker. So there are some people in here in that 3 hour range, but then there's another hump at that 3.5 to 4 hour. It's bimodal. It's two humps on our graph. So it refers to the peaks in the distribution. There's two peaks. Bimodal would have two peaks, obviously. Multimodal, there could be more than one peak. We could have, like on a test, if you have a 4-question exam, partial credit means there could be points in between, but chances are the scores are going to be grouped or clustered around having 0 correct, 1 correct, 2 correct, 7, 3 correct, or so on. So 25%, 50%, and whatever. So chances are your peaks are going to look like this. Hopefully they get a little larger at the higher ones, but who knows. So your distribution looks something like that. So that could be multimodal. What would a distribution be called if it had only one peak? Well, if it has only one peak, then it's either symmetrical or skewed, or unimodal. So bimodal distributions can occur when the data set consists of observations from two different kinds of individuals or two different possible outcomes. So when we look at this data set, what strikes you as the most distinctive characteristic here for class J? Well, they're kind of hard to pick out, but now that they're circled, you can see them out here, sitting way out on the ends. Those are called outliers, or unusual occurrences. There are values that sit way out away from the others. Now, in this one, we had one on each end, but we don't have to. We could have one just on one end or the other in many cases. There's big gaps between the main set of data and one or two data points. One way that we can decide that that's an outlier. Or if there's clusters. Sometimes we have outlier clusters. That's one of the things we got to look at a little more closely to see if there's a reason why there's numbers out there or if it is just a cluster of unusual values. Because sometimes outliers, even though they sit way out on the end, aren't unusual. So statistically, we have to decide whether they're truly an outlier or not. So let's look in context here. You must write your answer in reference to the context in the problem, using correct statistical vocabulary and using complete sentences. So when you summarize data, you have to make sure you are looking at the data and then referring back to what the original problem was that you were collecting that data to solve. Graphs for numerical data. Stem and leaf displays. So each number is split into two parts, the stem and then the leaf. The stem is usually just the first digit. If we have univariate numerical data, so in other words, we can only use this if we're displaying one variable. We can have back-to-back stem and leaf plots, but it has to be one variable for two different cases or two different applications. Used for small to moderate sized data sets. If you have a huge data set, a stem and leaf plot is not really practical. How do we construct it? Well, we take off that first digit or leading digit to make the stem, and then our other digits make the leaves. It works best if we have only two digits in our number or use only two digits. So we're going to record the leaf for each observation beside each corresponding stem value. If you have a long list of leaves behind a few stems, you can split the stems in order to spread out the distribution a little bit. So if you only have your first digits are only 2, 3, and 4, well, you can do 2, 2.5, 3, 3.5, 4, and 4.5 if you need to, just by putting a dot in there. Usually it's indicated by just putting a star or a dot at that point. Make sure you indicate what the units are here with a legend. So is that stem, is that the tens place so that the leaves are the ones? Or is that stem the ones place so that the leaves are the tenths? Or what does each stand for? So to describe each, you make sure you comment on the center and spread of the data. It actually is almost like taking the dot plot and turning it on its side. You can also create comparative stem and leaf plots or back-to-back stem and leaf plots where you have a stem down the middle and a leaf on each side. Remember the data sets collected in Chapter 1. How many piercings do you have? Would a stem and leaf plot work well for this distribution or not? Why or why not? It would work well here because we only have one set of data. So for the following set of data, our price per ounce for various brands of different brands of dandruff shampoo. Those are our prices per ounce, 32 cents, 21 cents, and so on. How would we construct the stem and leaf plot? Well, the appropriate stem would be the 3, 2, 2, 5, 1, 2, 3, 2. So I would start with 1, 2, 3, 4, 5 would be my stems. The leaves, well, that would be the second digit for each. Now, I like to put my numbers in order first. I would take my data set and put them in order first before I made my stem and leaf plot, just because it makes it easier on me, but you don't have to. The first one's a 32, so that goes after the 3 is the stem, the 2 goes after as a leaf. Now, when you do it this way, a lot of times you have to come back later and put these leaves in order, because you do want them in order from smallest to largest. So that puts the 2 there. That continuing with each leaf, so the 21 puts a 1 after the 2, a 9 after the 2, a 4 after the 5, the 17 puts a 7 after the 1. Notice they're not in order, so we do need to come back and put them in order before we're done. Now, right now, this distribution, if I described it, think of it as that dot plot put on its side. If I rotated it up, it would look something like this. Oops. It is skewed out to that higher end, or that right end. The middle seems to be right around the 20 to 30 range, probably in the high 20s it looks like. It's saying our median is 0.285, a range of 0.37, because the highest is 0.54, lowest is 0.17, just subtracting for the range. The median, there's 1, 2, 3, 4, 5, 6, 7, 8 values, so we count 1, 2, 3, 4. It's between the 28 and, well, I got to put those in order to make that work, don't I? That should be 1, 3, 8, 9. So 1, 2, 3, 4 between the 28 and 29. That's right, the 20.285 or 28.5 cents. And then this is positively skewed. The 54 cents would possibly be considered an outlier. Census Bureau projects the median age in 2030 for the 50 states and Washington, D.C. A stem and leaf plot here is to show it. So there's the median age for each state. So that's the middle number for each state. So there's 50 values put on here. The smallest one median age is one state has a median age of 29. The highest median age is actually 4 states have a median age that's going to be 46. Notice you really cannot see a distinctive shape here because there's only 3 categories. Since there's a high frequency for each categories, we can split them up. So you can say too high. In other words, that's the low is from 0 to 4, high is from 5 to 9. Notice they're the same size. So 2H would be the 5 to 9, so that's the 29. And then the 30, the 3 gets split into low and high. So the 0 through 4 and the 5 through 9. So you can see there's only a few that are there's 4 that are in the low 30s and a large number that's going to be in the high 30s. Same with the 40s get split up. Most of them are in the low 40s with only that 5 or so that are in the high 40 range. Now you get a much better distribution and you can see this is actually negatively skewed. It's a little stretched out on the low end for the smaller numbers. So given this data here on the percentage of primary school-age children who are enrolled in school for some countries, we're going to look at North Africa to Central Africa. We're going to create a comparative stem and leaf plot. So to do that, we have to make sure we have a stem that fits both sets of data, so it goes low enough for the lowest number of either set and high enough for the highest number of either set. So the appropriate stem here, let's see, I see 34. Is there anything lower than 34? Does not appear to be. So I have to make sure I go from at least a 3. Highest number, I see numbers in the 90s. I don't think anything over 90. So I have to go to 9. So 3, 4, 5, 6, 7, 8, 9 would be my stems. So there we can see we've gone 3 through 9. Then for each number, we've put we're going to just abbreviate each 54. Of course, they said was abbreviated just 4. So they're truncating it. They're not actually rounding it. They're just dropping the decimal. So 54.6 does not round up to 55. They're just truncating it to make it 54. You can round if you would like. It's totally something. You just have to make sure you specify that in the graph, whether the numbers were rounded or truncated to the nearest one. But like we said before, we really can only display 2 digits on the stem and leaf plot. The first digit is the stem, the second digit is the leaf. So there's our comparative plot, and we can see in Central Africa, a lot more lower numbers than in Northern Africa. Northern Africa has a lot more high numbers. So this comparative box plot helps you to describe how the 2 distributions relate to each other. So in this case, you might say that the median percentage of primary school age children that are enrolled in school is much smaller, is less in Central Africa than they are in Northern Africa, but the ranges are actually exactly the same. Both go from 34 to 98. Notice, by the way, that on the left side here, the numbers are put in reverse order. Smallest ones are in the center, and we work out going larger. On the right side, the smaller ones are in the center, and we go to the right, getting larger. That's an important note there. Histograms. We use these with, again, a single variable numerical data. We can construct it different depending on whether we have discrete or continuous data. For discrete, we just got low response discrete to high response discrete. If we have high response discrete where there's a large range of possible responses, that'll get treated similar to what we have for continuous data. So how do we construct it? We do that horizontal scale or axis with our possible responses, and then a vertical axis with our frequencies. And then above each possible, we draw that rectangle that represents the size of that frequency. With a histogram, we can either do frequency or relative frequency. So you can also then, from this, you can get comparisons on the center, spread, and other characteristics of the data. Comparative histograms can be used. You have to use 2 separate graphs with the same scale on the horizontal axis. For a comparable, you have that comparative bar graph or double bar graph where you put the bars side by side in the same graph. For a comparative histogram, you have to have 2 histograms, have the same number scale, and just have them stacked one above the other. You can't put the bars side by side. So in this example, we have queen honeybees mate shortly after they become adults. During the mating flight, the queen will usually take several partners, collecting sperm that she will store and use throughout the rest of her life. A study on honeybees provided the following data on the number of partners for 30 queen bees. So that's the number of partners they had during their mating flight. We're going to create a histogram based off of this data. So first we're going to draw a horizontal axis. Our range of data back here was from 0 to 12. 0 was the smallest. Actually, 1 was the smallest. 12 was the largest. So our axis has to make sure we go all the way up to 12. Our frequency, well, no numbers occurred more than 7 times, so we just have to make sure we go up to 7. We're doing the raw frequency here, not relative frequency. And we put in the graphs. There was one that mated once, one that mated twice, one that mated 3 times. Mating 4 times, there were 3 of them that mated 4 times, 2 that mated 5 times, and on down the line. Suppose we used relative frequency instead of raw frequency. Well, then the horizontal axis would go up to just whatever that highest relative frequency would be, in this case 0.25. Notice, by the way, the shape of the graph is exactly the same. The bar heights and all that other stuff are pretty much the same. So when do we use histograms? Again, that univariate numerical data. If we have continuous data now, we have to group the data into ranges or groups, categories. Again, like I mentioned, if we had a large range of responses for discrete data, we could also group them together, similar to what we're going to do here. Again, that's going to be on the horizontal, those groups are going to be on the horizontal axis and the frequencies on the vertical axis. And you can describe center, spread, and all that from the graph. So let's take a peek here. A study examining the length of hours spent watching TV per day for a sample of children age 1 and for a sample of children age 3 below. So this is actually going to be a comparative histogram. So this is saying from 0 to 2 hours is this bar. This is actually relative frequency instead of raw frequency as well. So it looks like about 27%. Between 2 and 4 hours here looks to be about 38 or 39%. And on down the line. Whereas for 3-year-olds, 0 to 2 hours, there's like 63%. So that's a much different shape. Both are skewed to the right, but the 1-year-olds are way less skewed. The 3-year-olds are way stretched out on the right, where the 1-year-olds are not. Their center is a little bit higher, whereas the 1-year or 3-year-olds, their center is in that 0 to 2 range. Notice the common scale. Again, notice on the bottom here we use the exact same categories, and we had the same scale on the vertical axis as well. We already kind of described the distribution, so we won't have to work on that. So the median number of hours spent watching TV per day was greater for the 1-year-olds. Again, their center was higher than the 3-year-olds. The distribution for the 3-year-olds was more strongly skewed to the right, although both were skewed to the right, than the 1-year-olds. But the two distributions had similar ranges. Went from 0 to 16 for both of them. So histograms with unequal intervals. This is something this textbook covers. A lot of textbooks say that a histogram has to have equal intervals. You can't have unequal intervals or it's not a valid histogram. And that's kind of the school that I've usually gone with. But for this course, we can use unequal histograms. And that's when the data is concentrated in certain areas and way spread out in others, so that you don't have some bars that are really huge next to ones that are really small. You can adjust the ranges of your intervals to make that work. What we're really looking at here then is more of a density than we are comparing frequencies. The density is your relative frequency for an interval divided by the width of that interval. Cumulative relative frequency plot. When to use? Used to answer questions about percentiles. So that cumulative frequency, building from 0 all the way up to the total. For relative frequency, it builds from 0 all the way up to 1 or 100%. Percentiles are the values of the percent of the data that is below a given observation. How do we construct it? Well, we use our frequency table and we make those relative frequencies, and we construct basically a bar graph or histogram off of that. So here's our relative frequency table. We're going to then add them up to get our cumulative relative frequencies. So the first one is the relative frequency is always the same as or cumulative relative frequency is always the same as the relative frequency for the first category. Then we add them up as we go down the table. So you can see the pattern is you just take the cumulative relative frequency for the previous, add the current one, and you get that as you go down. So what this is saying is, this is the 11 to 12 category here, that's saying that 89.5%, or a proportion of 0.895, is less than 12. Why isn't this value 1? Well, sometimes it's just round off errors when doing the relative frequencies. There might be some stray value out there that's larger than 14 or equal to 14. Generally, though, if that's not exactly 1, 0.999 is really close to 1. But if it's not exactly, generally the issue is there's round off errors in our percent calculations. So now we're going to create that cumulative relative frequency. We're going to plot a point for each interval starting at 4, 0. Oops, come on. So here, there's 4. We put a point there that those are starting. And of course, at 4 is our smallest number, so there's 0 numbers that are smaller than that. At 5 here, that was our 4 to 5 range. There's our value that we put there is that 0.052. At 6, it'd be the 0.155, and we keep building all the way up to 14. It's almost 1, or 0.999. And we connect them with a dot. So it's basically a line graph showing how the data builds. If this forms a perfectly straight line going up through there, then we're saying that means that the data is evenly distributed, that we increase about the same amount at each interval. We would expect it to be really small at first, rise slowly, then rise faster in the middle because of higher frequencies, and then tail off, which is kind of what this does. So this is telling us that that data is kind of that normally distributed, that bell shape or symmetrical curve. What proportion of the years had fallen rainfall amounts that were 9.5 or less? So here's 9, 9.5 would be right here. You trace that up and over. See, it's approximately 0.55 or 55%. Approximately 30% of the years had annual rainfall less than 1 amount. So then we're going to go 30% here, trace it over, and then down. That looks to be about 7.5 inches. Which interval of rainfall amounts had a larger proportion of years, 9 to 10 or 10 to 11? So now off of this, 9 to 10 is this range right here. 10 to 11 is this range. Now this, remember, is cumulative relative frequency, but the slope tells us. This is less slope here and more slope there. The larger slope is the category that had a larger frequency. So the intervals 10 to 11, because its slope is steeper, so they had a larger proportion in that period. Displaying bivariant numerical data. So data that has two different variables, we're going to use scatter plots, similar to that line plot that we just saw. We're going to put one range of numbers on the horizontal scale and the other on the vertical scale, and we're going to plot where they correspond. Then we describe the relationship between the variables, basically the shape that it takes on, linear or curved, quadratic, or whatever. Scatter plots are discussed a lot in Chapter 5 towards the end of the course, and looking at the regression lines and stuff like that is a big deal in statistics. Measurements collected over time at regular intervals. This is a time series plot. So it's one variable, one quantity that we're measuring about that variable, but what's changing is not some characteristic of the variable. What's changing is the point in time that we're measuring it. This is usually done on a line plot, by the way. So we construct it by putting the horizontal axis is the time, and then the values on the vertical axis. So we have a scale on the vertical axis to account for the values. And then we plot each point and connect them with a line. So here is an example of a line plot. This is actually a double line plot. We have two different things here. Actually, it's two different years compared, it looks like. So week 1, you can see there's the values is just over $100 for the 2001. Just under $200 for the 2002. If we go over here to like week 14, you can see that 2002 was about $235, where 2001 was over $250. So you can do a comparative line plot for time series data as well. So that is pretty much it for Chapter 3. We'll come back in a minute. We'll do another one for Chapter 4.